Subscribe to the channel so you don't miss out on any of these videos. Imagine this: the ground beneath your feet feels solid. The walls around you seem unyielding. But what if I told you that the very fabric of the universe, the thing holding everything together, is constantly bubbling, frothing, and shifting? Beneath the calm we see in the stars, space itself is seething with chaos at an unimaginable scale. This isn't science fiction. It's a genuine mystery, one that even the sharpest minds on the planet are still trying to untangle. A mystery called space-time foam. Space-time foam is where reality gets truly bizarre, a place where the predictable rules of physics seem to dissolve into randomness. It's a phenomenon that doesn't just stretch our understanding, it shatters it. What if space-time itself, the backdrop for everything we know, isn't smooth but wildly dynamic? What if, on the tiniest scales imaginable, space and time are behaving like a boiling pot of water, erupting with fluctuations that shape the very essence of existence? These are the questions scientists are daring to ask, and the answers might redefine everything we think we know about reality. But to really understand space-time foam, we need to dive deep into the quantum world, a realm so strange it almost defies logic. So, buckle up. What you're about to learn might change how you see the universe forever. To grasp the concept of space-time foam, let's start with the basics. In our day-to-day lives, space-time seems smooth and predictable. You move through it, objects occupy it, and clocks measure it. Einstein's theory of general relativity describes this space-time as a vast, continuous fabric that curves around massive objects, creating gravity. On this large scale, everything makes sense. But as you zoom in closer and closer, much smaller than an atom, smaller than the nucleus of an atom, you reach a point where the classical rules break down. This is where quantum mechanics comes in, and where space-time itself starts to look less like a calm ocean and more like a stormy sea. On these quantum scales, space-time is anything but smooth. It's a chaotic froth, constantly bubbling and fluctuating. Scientists call it foam, because that's the closest analogy we have to describe it. Just like the bubbles in a fizzy drink, the tiny pieces of space-time pop in and out of existence. This frothy behavior isn't visible to the naked eye, or even to the most advanced instruments we have today, but it's predicted by quantum mechanics. And the implications are staggering. To understand why space-time behaves this way, we need to talk about the concept of quantum fluctuations. At the smallest scales, energy doesn't stay still. It fluctuates wildly, creating temporary particles and waves out of nothingness. This is a fundamental principle of quantum mechanics, often referred to as the Heisenberg uncertainty principle. It states that you can never perfectly know certain pairs of properties, like position and momentum, at the same time. This uncertainty isn't just a limitation of our measurements, it's a feature of the universe itself. At the quantum level, it's impossible to pin down anything with absolute precision. And that includes space-time. Now, picture space-time as a grid. At large scales, it looks smooth, like graph paper. But as you zoom in, that grid starts to blur. The lines warp, twist, and sometimes vanish altogether. This blurriness is space-time foam. And it's not just an abstract idea, it has real, measurable consequences. It could help explain some of the biggest mysteries in physics, like why the universe is expanding the way it is or how black holes behave on a quantum level. But what does this frothiness really mean for the universe as a whole? Think of it this way: space-time foam is like the foundation of a building. If that foundation is constantly shifting and changing, then everything built on top of it is affected. On small scales, these fluctuations might seem minor, but they add up. They could influence how particles interact, how forces like gravity work, and even how time flows. In other words, space-time foam isn't just a curiosity. It's a key to understanding the very structure of reality. One of the most mind-bending aspects of space-time foam is the idea that it might allow for tiny wormholes to form and disappear in an instant. These wormholes are like shortcuts through space-time, connecting distant points in the universe. While these quantum wormholes would be far too small to travel through, their existence could have profound implications for how we understand space, time, and even causality. Could spacetime foam be the gateway to faster-than-light travel? Could it explain phenomena like quantum entanglement, where particles seem to interact instantaneously across vast distances? These are the kinds of questions researchers are grappling with. And then there's the connection to dark energy. Dark energy is the mysterious force driving the accelerated expansion of the universe. Could spacetime foam hold the answer to this cosmic puzzle? Some scientists believe that the constant fluctuations of spacetime could produce a kind of background energy, enough to push galaxies apart over billions of years. If this is true, then spacetime foam isn't just a theoretical construct, it's shaping the evolution of the cosmos itself. But for all the tantalizing possibilities, studying spacetime foam is incredibly difficult. It exists at scales so small that even our most advanced technologies can't directly observe it. Scientists rely on mathematical models and indirect evidence, like the behavior of particles in high-energy experiments, or the patterns of cosmic radiation left over from the Big Bang. Every new piece of data adds another layer to the puzzle, but the full picture is still out of reach. So, why does spacetime foam matter? Because it challenges us to rethink what we know about the universe. It forces us to confront the limits of our understanding and push beyond them. And it offers a glimpse into a realm where the rules of reality are rewritten, where the impossible becomes possible. This is the frontier of science, where the answers are as mysterious as the questions. If spacetime foam represents the foundation of the universe, then understanding it could unlock secrets that have eluded us for centuries. It's not just about satisfying curiosity, it's about fundamentally rewriting the rules of existence. To fully appreciate this, let's explore how this concept fits into the larger frameworks of physics and cosmology. At the intersection of general relativity and quantum mechanics lies a vast, unresolved tension. General relativity, Einstein's masterpiece, describes the universe on large scales, the motion of planets, the behavior of stars, and the curvature of spacetime caused by massive objects. It's a theory of the cosmos that works beautifully, until you shrink things down to quantum scales. That's where quantum mechanics takes over, a world where particles behave more like probabilities than physical objects, existing in multiple states simultaneously until observed. The problem is that these two theories don't play nicely together. General relativity assumes a smooth spacetime, while quantum mechanics predicts chaotic fluctuations at tiny scales. Spacetime foam is where these two views collide, and understanding it could help bridge this gap. Scientists have long searched for a theory of everything, a unified framework that combines general relativity and quantum mechanics. Spacetime foam could be the missing link. One of the most promising candidates for such a theory is string theory, which suggests that all particles are actually tiny, vibrating strings of energy. According to string theory, spacetime isn't continuous, it's made up of discrete, quantum chunks. This granular nature of spacetime aligns with the idea of spacetime foam, where these chunks constantly shift and change. String theory also introduces additional dimensions beyond the familiar three of space and one of time. Could spacetime foam be a manifestation of these hidden dimensions bubbling into our reality? It's a tantalizing thought. Another contender is loop quantum gravity, a theory that tries to quantize spacetime itself. In this framework, spacetime is made up of finite loops, like a woven fabric. The frothy nature of spacetime foam could be the result of these loops interacting at incredibly small scales. Loop quantum gravity predicts that spacetime is fundamentally discrete, much like the pixels on a screen. From a distance, the screen looks smooth, but up close, you see the individual dots. Spacetime foam might be the universe's version of those pixels. But what does this mean for time itself? We often think of time as a steady flow, ticking forward in a constant rhythm. But if spacetime foam is real, then time might not be as stable as it seems. At quantum scales, the fluctuations in spacetime could cause time to wobble, speeding up or slowing down in unpredictable ways. This idea challenges our most basic assumptions about causality and continuity. If time is frothy, then the very sequence of cause and effect could break down, opening the door to phenomena we can't yet imagine. And let's not forget the role of virtual particles, one of the strangest predictions of quantum mechanics. In the vacuum of space, particles and antiparticles constantly pop in and out of existence, annihilating each other almost immediately. This process, known as vacuum fluctuation, is a direct consequence of the uncertainty principle. Now, imagine these virtual particles interacting with the frothy structure of spacetime. Could their fleeting existence contribute to the bubbling nature of spacetime foam? Some physicists think so, and studying these interactions could reveal new insights into both quantum mechanics and cosmology. One of the most compelling areas of research involves black holes. These enigmatic objects already defy our understanding, with their singularities where spacetime itself seems to break down. If spacetime foam exists, it might offer a way to understand what happens inside a black hole. Some theories suggest that the quantum fluctuations of spacetime could prevent the formation of true singularities, replacing them with a chaotic, frothy core. This idea could also help resolve the so-called information paradox, the question of what happens to information that falls into a black hole. Could spacetime foam hold the key to preserving this information, encoded in its ever-shifting bubbles? Another avenue of exploration is the early universe. Moments after the Big Bang, the universe was a seething cauldron of energy and quantum fluctuations. Spacetime foam might have been especially prominent during this period, shaping the structure of the cosmos we see today. The patterns of galaxies, the distribution of dark matter, and even the properties of fundamental particles could all be traced back to this frothy beginning. By studying the cosmic microwave background, the faint afterglow of the Big Bang, scientists hope to find indirect evidence of spacetime foam, hidden in the tiny variations of temperature and density. And yet, for all its theoretical appeal, spacetime foam remains elusive. Detecting it directly is an enormous challenge, requiring technologies far beyond what we currently possess. One potential method involves studying the behavior of light as it travels across vast cosmic distances. If spacetime is frothy, it could cause tiny distortions in the paths of photons, creating a kind of quantum blur. Advanced telescopes and experiments like the Laser Interferometer Space Antenna, LISA, could one day measure these effects, providing the first glimpses of spacetime foam in action. As we continue to explore this concept, we're reminded of how much we still don't know about the universe. Spacetime foam is a reminder that reality is far stranger and more complex than it appears. It challenges us to look beyond the familiar and embrace the unknown, to push the boundaries of science and imagination. The more we delve into spacetime foam, the clearer it becomes that this concept may be the thread that ties together some of the greatest cosmic mysteries. Imagine for a moment the immense implications of understanding the quantum structure of spacetime. It could redefine everything we know about gravity, energy, and even the origins of the universe itself. Let's return to the intriguing question of how spacetime foam might interact with gravity. In Einstein's view, gravity isn't a force in the traditional sense, it's the warping of spacetime by massive objects. But if spacetime itself is frothy and unstable at quantum levels, how does gravity behave in such an environment? Could the frothiness of spacetime affect the strength or behavior of gravity in ways we haven't yet observed? Some physicists theorize that spacetime foam could be responsible for phenomena we currently attribute to dark energy and dark matter. These two mysterious forces make up the majority of the universe's mass-energy content, yet they remain largely unexplained. Dark energy is driving the universe's accelerated expansion, while dark matter appears to hold galaxies together. Could the constant quantum fluctuations of spacetime foam be influencing these cosmic scale effects? It's a tantalizing possibility, one that could redefine our understanding of the universe's structure and evolution. Consider this: spacetime foam might not just exist at quantum scales. Its effects could be amplified under extreme conditions, such as near black holes or during the earliest moments of the Big Bang. In these environments, the frothiness of spacetime might become more apparent, creating observable phenomena. For instance, near the event horizon of a black hole, spacetime is stretched to its limits. If spacetime foam is real, the intense gravitational forces could reveal its chaotic nature, potentially creating observable ripples or distortions. The study of gravitational waves, Ripples in spacetime caused by massive objects like merging black holes might also provide clues. These waves travel vast distances across the universe, passing through regions of spacetime where quantum fluctuations could distort their paths. By analyzing gravitational waves with extreme precision, scientists might detect subtle anomalies that hint at the existence of spacetime foam. One of the most exciting aspects of spacetime foam is its potential to unlock a new era of quantum gravity research. For decades, physicists have struggled to reconcile quantum mechanics with general relativity. Spacetime foam offers a natural framework for exploring how these two pillars of modern physics interact. If spacetime isn't smooth but instead consists of fluctuating, frothy bubbles, then our theories of gravity and quantum mechanics might need to be rewritten to account for this underlying structure. This brings us to the role of spacetime foam in quantum entanglement, a phenomenon so strange that Einstein famously called it spooky action at a distance. In entanglement, two particles become linked in such a way that the state of one instantly affects the state of the other, regardless of distance. Some researchers speculate that spacetime foam could serve as the medium through which this connection occurs. If spacetime is fundamentally frothy, then its quantum fluctuations might enable particles to remain interconnected across vast distances. But there's an even deeper mystery here. Could spacetime foam be the origin of reality itself? Some physicists believe that spacetime isn't just a backdrop for the universe, it's the very fabric of existence. If this is true, then spacetime foam could represent the quantum sea, from which all matter and energy emerge. In this view, particles, forces, and even time itself might arise from the frothy interplay of spacetime at its most fundamental level. This idea resonates with certain interpretations of quantum mechanics, particularly those involving the concept of the wave function. According to these interpretations, particles don't exist in definite states until they're observed. Instead, they exist as probabilities, described by a mathematical wave function. Could spacetime foam serve as the medium through which these probabilities collapse into reality? If so, then spacetime foam might not just describe the universe, it might create it. The implications of this are staggering. If spacetime foam is the foundation of reality, then understanding it could lead to a deeper understanding of existence itself. It could answer questions that have puzzled humanity for centuries. Why does the universe exist? What is the nature of time? And are there other realities beyond our own? Some researchers are even exploring the possibility that spacetime foam could enable the existence of parallel universes. In certain interpretations of quantum mechanics, every decision or event creates a branching universe, resulting in a multiverse of infinite possibilities. If spacetime is frothy and dynamic, then these branches might not just be theoretical, they could be embedded within the foam itself. In this view, spacetime foam could serve as the interface between our universe and countless others. The prospect of parallel universes raises profound questions about the nature of reality and our place within it. Could spacetime foam hold the key to understanding these alternate worlds? And if so, could we ever interact with them? These questions might seem like the stuff of science fiction, but they're grounded in the cutting-edge physics of spacetime foam and quantum mechanics. The search for evidence of spacetime foam is one of the most challenging and exciting endeavors in modern science. Experiments like the holometer, a high-precision interferometer designed to detect tiny fluctuations in spacetime, are pushing the boundaries of what we can observe. While these experiments haven't yet found definitive proof of spacetime foam, they represent an important step toward understanding this elusive phenomenon. As we continue to explore the concept of spacetime foam, we're reminded of how much we have yet to learn about the universe. It's a humbling and awe-inspiring journey, one that challenges us to rethink our most basic assumptions about reality. Spacetime foam isn't just a theoretical curiosity, it's a window into the deepest mysteries of existence, a reminder that the universe is far stranger and more wonderful than we can imagine. If we ever uncover the true nature of spacetime foam, it could revolutionize our understanding of the cosmos and perhaps even our role within it. To truly grasp the impact of this discovery, we must expand our thinking beyond the confines of traditional physics and delve into its broader implications for science, technology, and philosophy. One of the most exciting possibilities is how space-time foam might inform our understanding of the origins of the universe. The Big Bang, often seen as the ultimate starting point, still leaves many unanswered questions. What existed before the Big Bang, if anything? What mechanism triggered it? Some physicists suggest that space-time foam might offer a clue. If the frothy, quantum nature of spacetime existed before the Big Bang, it could have provided the conditions necessary for the rapid inflation of the universe. The chaotic fluctuations inherent to spacetime foam might have sparked the initial energy burst, setting the cosmos into motion. But the implications don't stop at the beginning of time. Spacetime foam could also hold clues about the ultimate fate of the universe. Today, we know the universe is expanding at an accelerating rate, driven by the mysterious force known as dark energy. If spacetime foam is influencing this expansion, understanding its properties could reveal whether the universe will continue to expand indefinitely, slow down, or collapse in a big crunch. It's even possible that spacetime foam might contribute to a cyclical model of the universe, where the cosmos alternates between periods of expansion and contraction. Another area ripe for exploration is the relationship between spacetime foam and quantum tunneling, a phenomenon where particles appear to pass through barriers they shouldn't be able to cross. Quantum tunneling is already a cornerstone of modern technology, enabling processes like nuclear fusion and the operation of semiconductors. If spacetime foam affects the probabilities underlying quantum tunneling, it might help us refine these technologies or develop entirely new ones. Imagine devices that could manipulate the frothy nature of spacetime itself, opening the door to unprecedented capabilities. And what about the potential for faster-than-light travel? In science fiction, this is often achieved through concepts like warp drives or wormholes, both of which rely on bending or manipulating spacetime. If spacetime foam is as dynamic and malleable as some theories suggest, it might offer a pathway to making these ideas a reality. By harnessing the fluctuations of spacetime foam, we might one day develop the ability to smooth out its frothiness in specific regions, creating stable pathways for interstellar travel. Of course, these possibilities raise profound ethical and philosophical questions. If we gain the ability to manipulate spacetime foam, what responsibilities will come with that power? Could such technology be used to alter the fabric of reality itself? And if spacetime foam is the foundation of the universe, does it contain the blueprint for everything that exists? These are not just questions for physicists. They are challenges that will require input from philosophers, ethicists, and society as a whole. Spacetime foam also forces us to confront the limits of human perception. Our everyday experience of reality is shaped by our senses and the scale at which we live. We perceive time as linear and space as continuous, but spacetime foam suggests that these perceptions are just approximations. At quantum scales, reality is far more chaotic and unpredictable. This realization is both humbling and exhilarating. It reminds us that the universe is far greater than our limited understanding and encourages us to keep pushing the boundaries of knowledge. In a broader sense, spacetime foam could redefine our relationship with the cosmos. For much of human history, we viewed the universe as something separate from ourselves, a vast, impersonal expanse. But if spacetime foam is the foundation of reality, then we are intrinsically connected to it. The particles that make up our bodies, the forces that govern our actions, and even the thoughts in our minds, all of these might ultimately arise from the frothy fabric of spacetime. This interconnectedness is a powerful reminder of our place in the cosmos and our shared origins with everything that exists. One intriguing philosophical implication is the idea that spacetime foam might be a form of cosmic consciousness. Some speculative theories suggest that the quantum fluctuations of spacetime foam could give rise to a kind of emergent intelligence, a mind, of the universe. While this idea is highly controversial and not supported by mainstream science, it raises fascinating questions about the nature of consciousness and its relationship to the cosmos. Could the frothy quantum fabric of spacetime serve as the substrate for some kind of universal awareness? If so, what might that mean for our understanding of life, intelligence, and existence? It's worth considering the role of spacetime foam in our quest for extraterrestrial life. If space-time foam is a universal property of the cosmos, then its effects would be felt everywhere, including on distant planets and in other galaxies. Understanding how space-time foam interacts with matter and energy could help us refine our search for life beyond Earth. It might also offer clues about the conditions necessary for life to arise and thrive, both here and elsewhere in the universe. As we continue to explore the mysteries of space-time foam, we are reminded of the profound interconnectedness of science, philosophy, and the human spirit. The quest to understand the quantum structure of the universe is not just an intellectual exercise. It's a journey that speaks to our deepest questions about who we are, where we come from, and where we're going. Space-time foam is more than a scientific concept. It's a doorway to the unknown, a challenge to our assumptions, and an invitation to imagine a universe far richer and more complex than we ever dreamed. This interconnectedness between space-time foam and the mysteries of existence ignites a sense of wonder about the profound unity of the universe. To truly grasp the nature of space-time foam, we must expand our curiosity beyond scientific equations and explore the philosophical and metaphysical dimensions it presents. This frothy fabric of space-time could be the thread that weaves together the physical, the metaphysical, and the abstract. One intriguing aspect to consider is the relationship between space-time foam and the arrow of time. Time, as we experience it, flows in a single direction, from past to future. This forward motion is intimately tied to the concept of entropy, the tendency for systems to move toward disorder. Yet, at the quantum level, time doesn't behave in the same straightforward way. Processes at this scale are often reversible, leading physicists to question the very nature of time itself. Could space-time foam, with its constant fluctuations and chaotic behavior, hold the key to understanding why time flows as it does? Could the frothy fabric of space-time serve as the quantum engine, driving the arrow of time? Furthermore, space-time foam might challenge our understanding of causality, the idea that events occur in a sequence of cause and effect. At the quantum level, the frothy nature of space-time introduces uncertainty and randomness, which could disrupt our classical notions of causality. This raises profound questions. Is the universe fundamentally deterministic, with every event leading predictably to the next? Or is it probabilistic, shaped by the chaotic fluctuations of space-time foam? If causality itself is a product of the frothiness of space-time, then our understanding of cause and effect might be little more than an illusion shaped by our macroscopic perspective. The implications of space-time foam also extend to the concept of information. In physics, information isn't just data, it's a fundamental property of the universe, tied to the arrangement of particles and the laws that govern them. Yet, the frothy, ever-changing nature of space-time foam suggests that information at the quantum level might not be as stable or permanent as we think. Could the fluctuations of space-time foam cause information to be lost or altered? If so, what might this mean for the laws of physics, which rely on the conservation of information? These questions are particularly relevant in the context of black holes, where the fate of information remains one of the greatest mysteries in modern physics. Another tantalizing possibility is that space-time foam might provide a natural explanation for quantum entanglement. Entanglement occurs when two particles become so deeply connected that the state of one instantly affects the state of the other, regardless of distance. This phenomenon has puzzled scientists for decades, challenging our understanding of locality and the speed of information transfer. If space-time foam is the underlying fabric of the universe, it might serve as the medium through which entangled particles communicate. The frothy, interconnected nature of space-time could create shortcuts or hidden pathways, allowing entangled particles to remain linked across vast distances. These hidden pathways could also have implications for the concept of wormholes, hypothetical tunnels through space-time that connect distant regions of the universe. Wormholes have long been a staple of science fiction, but they're also a serious area of study in theoretical physics. If space-time foam is as dynamic and interconnected as some theories suggest, it might naturally give rise to tiny, transient wormholes at quantum scales. These microscopic shortcuts could have profound implications for our understanding of space, time, and the possibility of faster-than-light travel. In fact, some physicists speculate that space-time foam might be the key to unlocking the secrets of interstellar travel. If we could learn to manipulate the frothy nature of spacetime, we might be able to create stable wormholes or other structures that allow us to traverse vast distances in an instant. This idea, while speculative, is rooted in the real physics of spacetime foam and represents one of the most exciting frontiers of scientific exploration. The study of spacetime foam also has profound implications for our understanding of the multiverse, the idea that our universe is just one of many. If spacetime is frothy and dynamic, it might naturally give rise to bubbles of reality, each representing a separate universe with its own physical laws and constants. In this view, our universe might be just one frothy bubble in an infinite sea of possibilities. This idea isn't just theoretical, it's supported by certain interpretations of quantum mechanics and cosmology, which suggest that the conditions for creating new universes could arise naturally from the fluctuations of spacetime foam. But what about the practical applications of understanding spacetime foam? While this might seem like an abstract and purely theoretical concept, its implications could be transformative for technology. If spacetime foam affects the behavior of particles and forces at quantum scales, understanding it could lead to breakthroughs in fields like quantum computing, where even tiny fluctuations can have significant effects. It might also inform the development of new materials or energy sources, harnessing the properties of spacetime foam to create technologies that seem like science fiction today. At its core, the study of spacetime foam is a journey into the unknown, a quest to understand the deepest mysteries of the universe. It challenges us to rethink our assumptions about reality and embrace the possibility that the cosmos is far stranger and more complex than we can imagine. Yet, this journey isn't just about uncovering the secrets of the universe. It's also about understanding ourselves. As we explore the frothy fabric of spacetime, we are reminded of our connection to the cosmos and our shared place within its vast, unfolding story. This connection between spacetime foam and our place in the universe is deeply humbling. At its core, spacetime foam suggests that the very fabric of reality is not a rigid, static construct but an ever-changing, dynamic interplay of forces and fluctuations. This realization forces us to rethink not only the mechanics of the cosmos but also our understanding of existence itself. One fascinating implication is how spacetime foam might interact with the concept of energy at the quantum level. Energy, as we know it, is neither created nor destroyed, but it can change forms. Within the frothy framework of spacetime foam, this principle might take on a new dimension. The quantum fluctuations inherent in spacetime foam could mean that energy itself is constantly being redistributed, with pockets of high and low energy arising spontaneously. These fluctuations might even provide a foundation for the emergence of matter in the universe, as particles could be born from temporary energy imbalances within the foam. This idea ties directly into the mystery of virtual particles, which appear and disappear in the vacuum of space. Virtual particles are a well-documented quantum phenomenon, but their existence raises questions about the nature of nothingness. If spacetime foam is the underlying structure of the universe, it could be the source of these virtual particles. The frothy fluctuations might act as a kind of quantum cradle, giving rise to these ephemeral particles and influencing their behavior. Understanding this relationship could help us unravel the true nature of the vacuum and redefine what we mean by empty space. Moreover, spacetime foam challenges the boundaries between the macroscopic and microscopic realms. On the surface, the frothy fabric of spacetime might seem relevant only at quantum scales, where its fluctuations dominate. However, these fluctuations could have cascading effects that influence larger structures, from atomic nuclei to galaxies. For instance, the behavior of spacetime foam could affect the formation of black holes, neutron stars, or even entire galaxy clusters. If spacetime foam plays a role in shaping these massive structures, its influence might extend far beyond the quantum world, impacting the universe on a cosmic scale. One particularly compelling area of exploration is the relationship between spacetime foam and gravity. Gravity, as described by Einstein's theory of general relativity, is the warping of spacetime caused by mass and energy. But general relativity doesn't account for the quantum scale behavior of spacetime. Could the frothy, fluctuating nature of spacetime foam provide a quantum explanation for gravity? Some physicists believe that spacetime foam might hold the key to unifying general relativity with quantum mechanics, a goal that has eluded scientists for decades. If we can reconcile these two fundamental theories, we might finally achieve a theory of everything, a framework that explains all forces and particles in the universe. This pursuit of a unified theory has profound implications for our understanding of reality. If spacetime foam is the bridge between the macroscopic and microscopic realms, it might reveal hidden connections between seemingly unrelated phenomena. For example, the same principles governing the frothy behavior of spacetime could also explain the behavior of particles, forces, and even consciousness. This interconnectedness suggests that the universe is not a collection of isolated parts but a cohesive, dynamic whole. Beyond theoretical physics, spacetime foam opens doors to entirely new ways of thinking about technology and innovation. Imagine devices that could harness the fluctuations of spacetime foam to generate energy, process information, or even manipulate the structure of reality. These advancements might seem like science fiction today, but they could become plausible as our understanding of spacetime foam deepens. Technologies based on spacetime foam could revolutionize fields like medicine, communication, and transportation, enabling us to achieve feats that were once thought impossible. But the pursuit of these possibilities also raises ethical and philosophical questions. If we gain the ability to manipulate spacetime foam, what responsibilities come with that power? How do we ensure that such technologies are used for the benefit of humanity rather than for destructive purposes? These questions are not just hypothetical, they are essential considerations as we stand on the brink of a new era in science and technology. Equally profound are the existential questions posed by spacetime foam. If the frothy fabric of spacetime is the foundation of reality, what does that say about the nature of existence? Are we, as conscious beings, simply temporary fluctuations within this frothy sea? Or is there something more permanent and meaningful about our existence? These questions challenge us to confront the deepest mysteries of life and the universe, encouraging us to look beyond the surface and explore the fundamental truths that shape our reality. As we continue to study spacetime foam, we are reminded of the importance of curiosity and imagination in scientific exploration. The frothy nature of spacetime is not just a puzzle to be solved, it is an invitation to wonder, to dream, and to expand our horizons. It reminds us that the universe is far richer and more complex than we can ever fully comprehend, and that our journey of discovery is only just beginning. Spacetime foam is not merely a concept for physicists to ponder in isolation. It is a gateway to understanding the universe in its entirety, from the smallest particles to the largest structures, from the origins of existence to its ultimate fate. It challenges us to rethink our place in the cosmos and to embrace the unknown with open minds and hearts. The journey into the mysteries of spacetime foam is not one that we undertake lightly, nor is it one that will yield answers quickly. But it is a journey worth pursuing, for it speaks to the very essence of what it means to be human, to question, to seek, and to wonder. And in the frothy, dynamic fabric of spacetime, we may yet find the answers to questions we have not yet dared to ask. This ongoing exploration of spacetime foam invites us to probe not just the fabric of the universe but the very boundaries of human understanding. It challenges us to confront the limitations of our current scientific models, which, while extraordinary in their achievements, remain incomplete. Spacetime foam represents a domain where our most well-established theories, relativity and quantum mechanics, clash, leaving a fertile ground for new ideas to emerge. One area where spacetime foam's influence becomes particularly fascinating is in the study of black holes. These cosmic enigmas are regions where gravity is so intense that nothing, not even light, can escape. At their core lies a singularity, a point where density becomes infinite, and the laws of physics as we know them break down. However, the frothy nature of spacetime foam suggests that this singularity might not be a point at all. Instead, quantum fluctuations could create a dynamic, ever-changing structure at the heart of a black hole, fundamentally altering our understanding of what happens in these extreme environments. This perspective also opens new doors for understanding the so-called information paradox of black holes. According to classical physics, information that falls into a black hole is lost forever, violating the principle of information conservation. But if space-time foam governs the quantum dynamics within black holes, it might allow for the preservation, or even the transformation, of information in ways we have yet to understand. Some theories propose that space-time foam could act as a kind of quantum ledger, subtly encoding and preserving information within its frothy fluctuations. The implications of this are profound. If information can survive the extreme conditions of a black hole, it suggests that the universe has an intrinsic mechanism for memory, a kind of cosmic record-keeping embedded in the fabric of spacetime itself. This idea resonates with concepts in quantum mechanics, such as the holographic principle, which posits that all the information within a volume of space can be represented on its boundary. Could spacetime foam be the medium through which this principle operates? Could its frothy structure serve as the screen on which the holographic universe is projected? Beyond black holes, spacetime foam also plays a role in the ongoing mystery of dark energy, the enigmatic force driving the accelerated expansion of the universe. Dark energy accounts for roughly 70% of the universe's total energy, yet its nature remains unknown. Some scientists speculate that the fluctuations of spacetime foam could be linked to dark energy, providing a quantum explanation for its effects. If the frothy structure of spacetime generates tiny bursts of energy on a cosmic scale, these bursts could collectively contribute to the universe's expansion. Similarly, spacetime foam might offer insights into the origins of the universe itself. The Big Bang theory describes the universe's rapid expansion from an incredibly dense and hot initial state, but it leaves unanswered questions about what preceded this event. If spacetime foam is a fundamental feature of reality, it might have existed even before the Big Bang, acting as the seed from which our universe emerged. The frothy fluctuations could have created the conditions necessary for the birth of spacetime, matter, and energy, offering a glimpse into the pre-Big Bang cosmos. Another intriguing possibility is that spacetime foam could be the mechanism behind quantum tunneling, a phenomenon where particles pass through energy barriers they seemingly shouldn't be able to cross. At first glance, quantum tunneling appears to defy logic, but if spacetime itself is frothy and dynamic, it might create temporary shortcuts, or weak points in energy barriers. These fluctuations could allow particles to tunnel through barriers, demonstrating yet another way in which spacetime foam shapes the quantum world. This connection between spacetime foam and quantum mechanics extends to the nature of wave-particle duality, one of the most puzzling aspects of quantum physics. Particles such as electrons and photons exhibit both wave-like and particle-like behavior depending on how they are observed. Could spacetime foam, with its chaotic and fluctuating nature, be the medium through which these dual properties manifest? If spacetime is inherently frothy, it might create conditions that allow particles to exist simultaneously as waves and discrete entities. The study of spacetime foam also forces us to rethink our understanding of boundaries and dimensions. In our everyday experience, we perceive the universe as having 3 spatial dimensions and 1 time dimension. But spacetime foam suggests that, at quantum scales, these dimensions might not be as distinct or stable as they seem. The frothy fluctuations could blur the boundaries between dimensions, creating a dynamic, multidimensional structure that defies classical categorization. This idea aligns with certain interpretations of string theory, which propose that additional dimensions exist but are compactified or hidden at quantum scales. Could spacetime foam be the key to unlocking these hidden dimensions? If so, it might provide a framework for understanding phenomena that currently elude explanation, such as the behavior of gravity at quantum scales or the unification of all fundamental forces. By studying the frothy nature of spacetime, we might gain access to a deeper layer of reality, one that reveals the true structure of the cosmos. Yet, despite its profound implications, spacetime foam remains an elusive concept. Observing or measuring its effects directly is an enormous challenge, as its influence operates at scales far smaller than we can currently probe. However, advancements in technology and experimental techniques are bringing us closer to this frontier. For example, experiments with high-energy particle collisions or observations of cosmic phenomena like gravitational waves might provide indirect evidence of space-time foam's existence. These efforts represent the cutting edge of science, pushing the boundaries of what we can observe and understand. As we continue to explore the mysteries of space-time foam, we are reminded of the vastness and complexity of the universe. The frothy fabric of space-time serves as a metaphor for our quest for knowledge, an ever-shifting, dynamic pursuit that requires both humility and imagination. Each fluctuation of the foam represents a new possibility, a new question to explore, and a new opportunity to expand our understanding of reality. In many ways, the study of space-time foam encapsulates the essence of human curiosity. It is a journey into the unknown, driven by the desire to uncover the fundamental truths that govern our existence. It challenges us to think beyond the limits of our current understanding and to embrace the complexity and beauty of the cosmos. And in doing so, it reminds us that the universe is not just a collection of facts to be learned but a source of endless wonder to be experienced. This journey into space-time foam invites us to reconsider the very notion of reality itself. If the fundamental structure of the universe is dynamic, frothy, and constantly fluctuating, then what we perceive as solid and stable might be nothing more than an illusion created by our limited perspective. The frothiness of space-time challenges the classical view of a universe governed by deterministic laws and suggests instead a cosmos rich with uncertainty, potential, and creativity. One of the most exciting aspects of space-time foam is its potential to bridge the gap between quantum mechanics and general relativity. These two pillars of modern physics describe vastly different realms: the quantum world of the very small and the relativistic world of the very large. Yet, they remain fundamentally incompatible, with each theory breaking down under the conditions described by the other. Space-time foam, existing at the intersection of these domains, might offer a pathway toward their unification. By studying the frothy nature of space-time, scientists could uncover the elusive theory of everything that has long been the holy grail of physics. This unification could have profound implications for our understanding of the universe. For example, it might reveal new insights into the nature of time itself. In classical physics, time is often treated as a linear progression, a steady march from past to future. But the frothy fluctuations of space-time suggest a more complex picture, where time is not a smooth continuum but a dynamic and malleable construct. These fluctuations might create local distortions in time, causing it to flow differently in different regions of the cosmos. Such a concept resonates with the time dilation effects predicted by relativity but extends them into the quantum realm. This reimagining of time could also shed light on some of the universe's greatest mysteries, such as the nature of causality. In our everyday experience, causes precede effects in a predictable sequence. But at the quantum level, the frothy nature of space-time might blur this relationship, creating situations where causes and effects are intertwined in ways that defy classical logic. This phenomenon, often referred to as quantum entanglement of space-time, could offer new insights into the interconnectedness of the universe and the nature of reality itself. Moreover, space-time foam might provide a framework for understanding phenomena that seem to transcend the boundaries of conventional science. For instance, some researchers have speculated that the frothy structure of space-time could create temporary wormholes or shortcuts between distant points in the universe. These quantum-scale wormholes could, in theory, allow for instantaneous communication or travel across vast distances, challenging our current understanding of space and time. While such ideas remain speculative, they highlight the transformative potential of studying space-time foam. By delving into the frothy fabric of the cosmos, we might uncover new principles that not only reshape our understanding of physics but also inspire revolutionary technologies. Imagine a future where we harness the dynamic nature of space-time to develop quantum computers, teleportation devices, or even methods for exploring other dimensions. The possibilities are as boundless as the universe itself. Yet, with this potential comes a sense of humility. Space-time foam reminds us that our current understanding of the universe is but a fragment of a much larger picture. Each discovery we make reveals new layers of complexity, challenging us to look deeper and think more creatively. The frothy nature of spacetime is a testament to the richness and intricacy of the cosmos, a reminder that even the smallest scales of reality hold infinite wonders. As we probe the mysteries of spacetime foam, we are also confronted with profound philosophical questions. What does it mean to live in a universe that is fundamentally dynamic and uncertain? How do we reconcile our desire for stability and predictability with the inherent chaos of the quantum world? And what role do we, as conscious beings, play in this frothy, ever-changing cosmos? These questions invite us to reflect on the nature of knowledge itself. The study of spacetime foam is not just a scientific endeavor. It is a journey into the unknown that challenges us to expand our perspectives and embrace the mystery of existence. It is a reminder that science is not just about finding answers but about asking questions that push the boundaries of what we know and open the door to new possibilities. The exploration of spacetime foam is a celebration of curiosity, imagination, and the human spirit. It is a testament to our ability to look beyond the surface of reality and uncover the hidden layers that shape our existence. And it is a reminder that, no matter how much we learn, the universe will always hold mysteries that inspire wonder and awe. As we continue this journey, we are reminded that the frothy fabric of spacetime is not just a scientific concept but a metaphor for the infinite potential of discovery. Each fluctuation of the foam represents a new opportunity to learn, to grow, and to connect with the cosmos. And in that sense, spacetime foam is not just the foundation of the universe, it is the foundation of our quest to understand it. The frothy fabric of spacetime invites us to dive deeper into the smallest, most elusive corners of reality. It is a terrain where quantum mechanics reigns supreme, shaping the universe in ways that are as mysterious as they are profound. To truly grasp the significance of spacetime foam, we must confront the strange and counterintuitive principles that govern the quantum world. At its heart, quantum mechanics describes a reality where particles behave both as particles and waves, existing in a state of superposition until observed. This phenomenon, already perplexing, becomes even more intricate when applied to the very fabric of spacetime. The frothy nature of spacetime suggests that these quantum properties are not confined to particles but extend to the structure of the universe itself. In this view, spacetime is not a fixed backdrop against which events unfold but an active participant in the cosmic drama, constantly shifting and evolving. This dynamic vision of spacetime raises fascinating questions about the relationship between matter, energy, and the fabric of the cosmos. One of the most intriguing aspects of spacetime foam is its potential role in generating virtual particles. These are particles that pop in and out of existence within the quantum vacuum, a process driven by the constant fluctuations of spacetime. Though fleeting, these virtual particles have real effects, contributing to phenomena such as the Casimir effect and Hawking radiation. The existence of virtual particles also has profound implications for the conservation of energy. In classical physics, energy is a fixed quantity that cannot be created or destroyed. Yet, in the frothy quantum realm, energy appears to be borrowed from spacetime itself, allowing virtual particles to briefly exist before annihilating one another. This borrowing and returning of energy challenge our understanding of fundamental principles, suggesting that spacetime is not merely a passive framework but an active participant in the universe's evolution. These ideas also intersect with the concept of quantum tunneling, a phenomenon where particles traverse barriers that, according to classical physics, should be impenetrable. In a frothy spacetime, the boundaries between regions of space and time may become blurred, creating opportunities for quantum tunneling on a cosmic scale. Such tunneling events could have played a crucial role in the early universe, enabling the rapid inflation that shaped the cosmos as we know it today. The implications of spacetime foam extend far beyond the quantum vacuum, influencing phenomena on both microscopic and cosmic scales. For example, the frothy structure of spacetime could help explain the emergence of black holes, regions where gravity becomes so intense that spacetime itself is warped beyond recognition. Within the event horizons of black holes, the frothiness of spacetime might reach an extreme, creating conditions where quantum effects dominate and new physics emerges. Some researchers have even speculated that spacetime foam could hold the key to understanding dark energy, the mysterious force driving the accelerated expansion of the universe. If spacetime is inherently frothy, with constant fluctuations, these fluctuations might contribute to the overall energy density of the cosmos, manifesting as dark energy. This idea, while still in its infancy, offers a tantalizing glimpse into how the quantum nature of spacetime could shape the universe on the largest scales. The frothy nature of spacetime also invites us to reconsider the concept of dimensions. In classical physics, we experience the universe as having 3 spatial dimensions and 1 temporal dimension. However, the quantum foam suggests that additional dimensions might exist, hidden within the froth at scales too small to detect. These hidden dimensions could provide the missing links needed to unify quantum mechanics and general relativity, offering a pathway toward a deeper understanding of the universe. One theory that explores these hidden dimensions is string theory, which posits that the fundamental building blocks of reality are not particles, but vibrating strings of energy. In this framework, the frothy structure of spacetime could serve as the stage upon which these strings vibrate, giving rise to the particles and forces that shape the universe. The interplay between spacetime foam and string theory could unlock new insights into the nature of gravity, the origin of the cosmos, and the fundamental structure of reality. Despite the progress made in understanding spacetime foam, many questions remain unanswered. How do these fluctuations interact with the observable universe? What role do they play in shaping the evolution of galaxies, stars, and planets? And how can we study such phenomena, given their incredibly small scales and fleeting nature? These challenges highlight the need for innovative approaches and technologies that can probe the quantum fabric of the cosmos. One promising avenue for exploring spacetime foam is the study of gravitational waves, ripples in spacetime caused by massive cosmic events such as the collision of black holes. These waves offer a direct glimpse into the dynamics of spacetime, potentially revealing the frothy structure that underlies its smooth appearance. By studying the patterns and frequencies of gravitational waves, scientists might uncover evidence of the quantum fluctuations that define spacetime foam. Another potential tool for investigating spacetime foam is the development of advanced particle accelerators and detectors capable of probing the quantum vacuum at unprecedented scales. These instruments could help scientists observe the effects of spacetime fluctuations on particles and forces, providing new insights into the interplay between quantum mechanics and relativity. Such experiments could also test theoretical predictions about the behavior of spacetime foam, offering a way to bridge the gap between theory and observation. The exploration of spacetime foam is not just a scientific endeavor but a profound journey into the nature of existence itself. It challenges us to rethink our assumptions about reality, to embrace uncertainty, and to recognize the interconnectedness of all things. By studying the frothy fabric of spacetime, we are not only uncovering the secrets of the cosmos but also deepening our understanding of our place within it. This quest is a testament to the power of human curiosity and imagination. It reminds us that, no matter how much we learn, there will always be mysteries to explore and questions to ask. And in that sense, the study of spacetime foam is not just about understanding the universe. It is about celebrating the boundless potential of discovery. The mystery of spacetime foam takes us into realms of speculation that stretch the limits of human imagination. Its frothy, dynamic structure forces us to reconsider fundamental questions about the universe. What is space? What is time? And how do they arise from the deeper fabric of reality? As researchers dive further into these mysteries, the implications become increasingly profound, touching on the origins of the cosmos, the nature of consciousness, and the ultimate fate of the universe. One area of intense focus is the relationship between spacetime foam and the Big Bang. The birth of the universe, as we currently understand it, was a moment of incredible density and energy, when all the matter and space in existence were compressed into an unimaginably small point. In such extreme conditions, the frothy structure of spacetime may have played a critical role. Quantum fluctuations within the foam could have provided the seeds for cosmic inflation, the rapid expansion that set the stage for the formation of galaxies, stars, and planets. These quantum fluctuations might also explain why the universe appears to be uniform on large scales but exhibits intricate structures, such as galaxy clusters, on smaller scales. Tiny variations in the density of spacetime foam could have been amplified during inflation, creating the patterns we see in the cosmic microwave background radiation, the faint afterglow of the Big Bang. This connection between the frothy quantum realm and the vastness of the cosmos underscores the unifying power of spacetime foam as a concept. But the implications of spacetime foam extend beyond the past and into the future. If the universe is fundamentally frothy and dynamic, then its evolution may not be as predictable as classical physics would suggest. The frothiness of spacetime could lead to unexpected phenomena, such as sudden changes in the rate of cosmic expansion, or the emergence of new regions of spacetime with different physical properties. These possibilities challenge our understanding of the universe's long-term fate and raise intriguing questions about its ultimate destiny. For instance, could the frothy nature of spacetime eventually cause the universe to bubble into entirely new forms of existence? Some theories suggest that the frothiness of spacetime could lead to the creation of pocket universes within our own cosmos, each with its own unique laws of physics. This idea, often referred to as the multiverse hypothesis, posits that our universe is just one of countless others, all connected by the frothy fabric of spacetime. If true, this would radically alter our understanding of reality, transforming the universe from a singular entity into a vast, interconnected web of possibilities. The study of spacetime foam also has profound implications for the nature of black holes. These enigmatic objects, with their extreme gravitational forces, warp spacetime to the point where not even light can escape. Within a black hole's event horizon, the frothy nature of spacetime may become so pronounced that it creates a quantum storm, where the distinctions between space, time, and matter dissolve. This chaotic environment could hold the key to understanding what happens to information that falls into a black hole, a question that has puzzled physicists for decades. Some researchers have proposed that the frothy structure of spacetime could prevent the complete collapse of matter within a black hole, creating a quantum firewall, or even a new kind of stable structure at the core. Others speculate that black holes might act as gateways to other regions of the cosmos, with spacetime foam facilitating the formation of quantum wormholes. These ideas remain speculative but offer tantalizing glimpses into the potential interplay between quantum mechanics and gravity. Another fascinating aspect of spacetime foam is its potential connection to dark matter and dark energy, two of the most mysterious components of the universe. Dark matter, which makes up about 27% of the universe, exerts gravitational effects on visible matter but does not interact with light. Dark energy, accounting for roughly 68% of the universe, drives its accelerated expansion. Could these phenomena be manifestations of the frothy nature of spacetime? Some theories suggest that dark matter might arise from the quantum fluctuations of spacetime foam, creating particles or structures that interact only weakly with ordinary matter. Similarly, dark energy could be linked to the energy density of the frothy vacuum itself, with the constant fluctuations of spacetime generating a small but pervasive force that pushes the universe outward. While these ideas remain highly speculative, they highlight the potential of spacetime foam to provide a unified framework for understanding some of the universe's deepest mysteries. As we probe the nature of spacetime foam, we are also confronted with questions about the limits of human knowledge. Can we ever truly understand the frothy fabric of the cosmos, given its complexity and scale? What tools and methods will be needed to study phenomena that occur on scales billions of times smaller than an atom? These challenges remind us that the exploration of spacetime foam is not just a scientific endeavor but a philosophical and existential one. The quest to understand spacetime foam is a testament to the power of human curiosity and ingenuity. It challenges us to look beyond the surface of reality and delve into the depths of the unknown. Each discovery we make brings us closer to understanding the universe, yet also reveals new layers of complexity and wonder. In this sense, spacetime foam is not just a scientific concept but a symbol of the infinite possibilities that lie within the cosmos. As we continue to explore this frothy frontier, we are reminded of our place within the universe, a small but significant part of a vast, dynamic, and interconnected whole. The study of spacetime foam is a journey that invites us to embrace the mystery, to ask questions, and to celebrate the beauty of discovery. It is a journey that will undoubtedly shape the future of science and our understanding of existence itself. The exploration of space-time foam is not just a theoretical pursuit but one with potential practical implications that could revolutionize our understanding of the universe and the technologies we develop. If we were to somehow manage to grasp the intricacies of this quantum structure, it could potentially open up entirely new realms of physics, enabling breakthroughs in energy, communication, and perhaps even space travel itself. However, as it stands, the road to these discoveries is still clouded in uncertainty, but the search continues. Let's consider, for a moment, the deeper mysteries of the quantum foam in relation to the fabric of reality itself. Space-time foam suggests that the very stuff of the universe at the quantum level is in a constant state of flux, where particles spontaneously emerge and vanish in an incessant dance. This chaotic motion and energy may explain certain phenomena in quantum mechanics, such as the spontaneous creation of particle-antiparticle pairs. These particles pop in and out of existence so rapidly that they defy the traditional laws of physics. This notion brings us closer to the fundamental question of whether the vacuum of space is truly empty. Traditionally, space was thought to be a void, an empty expanse. But space-time foam suggests that even the emptiest vacuum is far from inert. It's a seething, bubbling cauldron of quantum fluctuations where space itself isn't empty but filled with dynamic energy that constantly fluctuates. This isn't just a philosophical notion, it has real-world implications, such as the Casimir effect, where two uncharged, parallel plates placed in a vacuum experience an attractive force. This phenomenon can be traced back to the fluctuations in the quantum vacuum that exists between the plates. However, this frothy picture of space-time becomes even more interesting when considering how it might influence larger cosmic events. Some physicists speculate that the early universe's violent expansion during the Big Bang could have been directly impacted by the quantum foam. During this period, the very fluctuations within space-time could have helped to seed the growth of galaxies, stars, and cosmic structures by creating tiny inhomogeneities that were stretched over time. As the universe expanded, these quantum fluctuations, initially imperceptible, became the foundational variations that would later lead to the formation of the universe we see today. This link between space-time foam and the cosmic structures of the universe, though speculative, highlights the potential for a much deeper connection between quantum mechanics and cosmology. If space-time foam can influence the universe on such a large scale, perhaps the reverse is true as well. Perhaps the large-scale structure of the universe can tell us more about the fundamental nature of space-time itself. This cyclical relationship between the micro and macrocosmos is something we're only beginning to explore. Moreover, space-time foam challenges some of the most foundational ideas in modern physics. For instance, one of the biggest puzzles in physics is the search for a unified theory, a theory that can reconcile quantum mechanics, which governs the smallest particles in the universe, with general relativity, which governs the massive cosmic structures like planets, stars, and galaxies. Quantum foam plays a crucial role in this puzzle, offering clues to a possible bridge between the two. The assumption that space-time is smooth and continuous breaks down at the quantum scale, where space-time becomes granular and discontinuous. By recognizing space-time as a frothy, fluctuating field, we can begin to imagine a theory that might unify quantum mechanics and general relativity, something that has eluded scientists for over a century. It might lead to breakthroughs in understanding how gravity works at the quantum level and could offer solutions to long-standing problems such as the behavior of singularities inside black holes. The intriguing idea of a quantum foam at the heart of these cosmic objects hints at a deeper, more profound understanding of the universe's inner workings, possibly leading to a new era in theoretical physics. But there's more to space-time foam than just its theoretical implications. Understanding its structure may also help us solve some of the most confounding mysteries of modern cosmology, such as the nature of dark energy and dark matter. Dark energy, which is responsible for the accelerated expansion of the universe, might be connected to the vacuum energy inherent in space-time foam. If space-time fluctuates at the quantum level, these fluctuations could contribute to the cosmic acceleration we observe today, pushing the universe to expand faster than previously predicted. Similarly, dark matter might find an explanation in the quantum foam hypothesis, with unseen particles emerging from the frothy structure that interact only weakly with regular matter. On a more practical level, studying spacetime foam could potentially lead to breakthroughs in technology, particularly in areas like quantum computing and energy storage. Quantum fluctuations, as unpredictable and chaotic as they are, might hold the key to harnessing previously inaccessible forms of energy or information. If we can better understand how spacetime behaves at the smallest scales, it might be possible to engineer technologies that take advantage of these fluctuations, leading to new forms of computing or even novel methods for transmitting information faster than the speed of light. One such area where spacetime foam could prove to be revolutionary is in the realm of quantum teleportation, a concept that has already made waves in the scientific community. In theory, quantum teleportation involves transmitting the quantum state of a particle from one place to another without physically moving the particle itself. This mind-bending process could be made possible by better understanding the quantum structure of spacetime, especially the fluctuations that occur within the foam. If we can manipulate these fluctuations, it might one day be possible to teleport information across vast distances, leading to near-instantaneous communication. Space travel, too, might benefit from insights into the quantum foam. While interstellar travel may seem impossibly distant, the principles that govern the universe on a quantum scale could eventually allow us to develop propulsion systems that operate in entirely new ways. Concepts like wormholes, hypothetical tunnels through spacetime that connect distant parts of the universe, are still very much theoretical, but they could be linked to the quantum structure of spacetime. If spacetime is, in fact, frothy and dynamic, the possibility of manipulating these holes in spacetime might not be as far-fetched as it seems. Ultimately, our understanding of spacetime foam may help us answer some of the biggest questions about existence. What is the true nature of reality? How did the universe begin, and how will it end? Can we uncover the secrets hidden within the fabric of spacetime itself? As we continue to explore these mysteries, the answers may not only change our understanding of the cosmos, but also revolutionize the way we perceive space, time, and the very nature of the universe. The exploration of spacetime foam offers a glimpse into the potential future of physics and technology, where the boundaries between theoretical and practical applications might blur. Understanding the very structure of spacetime could open up possibilities that were once reserved for science fiction. While these ideas may seem outlandish now, the progress of science often operates in surprising ways, transforming abstract concepts into reality. For example, in the realm of quantum mechanics, phenomena that seem entirely disconnected from the tangible world have led to some of the most groundbreaking discoveries and technologies in history. Take quantum entanglement, for instance, a phenomenon where two particles become linked in such a way that the state of one immediately affects the state of the other, regardless of the distance between them. This seemingly paradoxical connection between particles was once considered a strange and baffling curiosity, but today, it's the foundation of emerging technologies like quantum computing and quantum encryption. The exploration of spacetime foam may follow a similar trajectory, with abstract principles leading to profound technological advancements that are difficult to imagine today. One of the most significant aspects of spacetime foam is its role in the ongoing quest to understand the very nature of gravity. General relativity, which describes how gravity works at large scales, has been incredibly successful in explaining the motion of planets, stars, and galaxies. However, when we attempt to apply the principles of general relativity to the quantum realm, the theory breaks down. The smooth fabric of spacetime that general relativity relies on isn't compatible with the chaotic nature of the quantum world. This creates a massive gap in our understanding of how gravity operates at the smallest scales, particularly inside black holes or during the Big Bang, where both quantum mechanics and general relativity are at play. This is where spacetime foam enters the conversation. By proposing that spacetime is not smooth but instead constantly fluctuating at the quantum level, the idea of quantum foam offers a way to reconcile these two seemingly incompatible theories. If spacetime is granular and fluctuating, it could provide the necessary framework to understand how gravity behaves at quantum scales. It's possible that this fluctuating structure of spacetime could be the key to resolving some of the most perplexing problems in modern physics, such as the nature of black holes and the behavior of singularities. Consider black holes for a moment. These mysterious objects, with their intense gravitational fields, have long been a point of fascination for physicists. Inside the event horizon, the boundary beyond which nothing, not even light, can escape, there exists a point of infinite density known as a singularity. At this singularity, the laws of physics as we know them break down, and our understanding of the universe's behavior ceases to make sense. The idea that spacetime itself could be foamy and granular offers a potential explanation for what happens at these extreme conditions. Perhaps the fluctuations in spacetime near a black hole's singularity cause the normal laws of physics to behave in unpredictable ways, allowing us to reconsider the very nature of these enigmatic objects. Spacetime foam may also hold the answers to some of the most fundamental questions about the origins of the universe. The Big Bang, which marks the beginning of our universe, remains one of the most profound mysteries in cosmology. Traditional theories suggest that the universe began as an infinitely dense point, a singularity that rapidly expanded in an event known as cosmic inflation. However, the exact mechanisms behind the Big Bang are still unclear. Could the fluctuations in the quantum foam have played a role in triggering this monumental event? If spacetime is granular at the quantum level, then the initial conditions of the universe could have been shaped by these fluctuations, leading to the rapid expansion of the universe we observe today. These quantum fluctuations might have seeded the formation of galaxies and other cosmic structures, creating the large-scale patterns that define the universe's structure. This raises an even more intriguing possibility. Could spacetime foam provide a link between the quantum world and the larger structure of the universe? If the quantum fluctuations in spacetime can influence cosmic events like the formation of galaxies and stars, then understanding these fluctuations might allow us to gain deeper insights into the fundamental nature of the universe. It's possible that spacetime foam is not just the curiosity of the quantum world but a key player in the very fabric of the cosmos, influencing everything from the smallest particles to the largest structures in the universe. But the implications of spacetime foam aren't confined to the distant past or faraway galaxies. The very presence of quantum fluctuations in spacetime could have a direct impact on our everyday lives, potentially leading to new technologies that harness these phenomena. As we continue to explore the properties of spacetime foam, we might discover ways to manipulate the quantum fluctuations of spacetime for practical purposes. For instance, quantum computing, which relies on the strange properties of quantum mechanics, could potentially be enhanced by understanding how spacetime itself behaves at the quantum level. This could lead to the development of faster, more powerful computers that operate on principles entirely different from the classical computers we use today. Similarly, the concept of spacetime foam could revolutionize our understanding of energy and propulsion. If spacetime is indeed frothy and fluctuating, then it might be possible to tap into these fluctuations as a source of energy. This idea is still purely speculative, but the potential for harnessing the quantum fluctuations of spacetime could lead to entirely new forms of energy production. In the future, we may even find ways to manipulate spacetime itself, creating propulsion systems that allow us to travel vast distances across the universe in a fraction of the time it currently takes. The search for answers to these profound questions is not just the domain of physicists and scientists. It's a journey that involves all of us. The mysteries of spacetime foam and the quantum structure of the universe challenge our understanding of reality itself. As we continue to probe the depths of the cosmos, we may uncover truths that completely reshape our view of the universe, transforming everything from our understanding of the laws of physics to our place in the vast expanse of space. Ultimately, the quest to understand spacetime foam is more than just an academic pursuit. It's a journey that might redefine the very nature of existence. It raises questions that are as old as philosophy itself. What is the true nature of reality? What lies beyond the limits of our current understanding? Can we ever hope to fully comprehend the complexities of the universe? Or will there always be mysteries beyond our reach? These questions remain unanswered, but as we continue to explore the nature of spacetime, we are one step closer to understanding the fundamental structure of the universe, and perhaps, our place within it. As we push further into the realms of space-time foam, there's another layer of complexity to consider: the potential for quantum gravity. Currently, our understanding of gravity is framed by Einstein's general theory of relativity, which describes gravity as the curvature of space-time caused by massive objects. This framework has been highly successful in explaining the gravitational interactions at macroscopic scales, from the orbits of planets to the bending of light around massive galaxies. However, when we attempt to understand gravity at the microscopic level, on the scale of atoms or subatomic particles, general relativity begins to break down. This is where quantum mechanics comes into play, offering a completely different perspective on the nature of the universe at small scales. The challenge arises because quantum mechanics operates under a set of rules that are vastly different from those of general relativity. Quantum mechanics deals with particles that exist in probabilistic states, and the interactions between them are governed by principles like superposition, where particles can exist in multiple states simultaneously. General relativity, on the other hand, assumes that spacetime is a smooth and continuous fabric. These two frameworks simply don't mesh when we try to explain phenomena like the behavior of gravity at the quantum level. Spacetime foam, with its fluctuating nature at the smallest scales, could be the missing piece that helps us reconcile these two theories. If spacetime is not smooth, but instead composed of minute quantum fluctuations, it might provide a way to unify the theories of general relativity and quantum mechanics. The key lies in understanding how the fluctuations of spacetime foam interact with the particles and forces that govern the quantum world. In a sense, spacetime foam could be the quantum fabric that underpins both gravity and the other fundamental forces of nature, offering a way to bridge the gap between quantum mechanics and relativity. This pursuit of quantum gravity is not a mere academic curiosity. It could have profound implications for our understanding of the universe and our ability to manipulate the forces of nature. If we can truly grasp the mechanics of quantum gravity, we could unlock new ways to control the fundamental interactions of the universe. For example, gravity is currently the weakest of the fundamental forces, and yet it governs the behavior of objects on large scales, from planets to galaxies. If we understood gravity at the quantum level, it's possible that we could manipulate it in ways that would allow for previously unimaginable feats of technology, from creating anti-gravity devices to developing new forms of energy. However, the path to understanding quantum gravity is fraught with challenges. Current experimental techniques and technology are not yet advanced enough to probe the fluctuations in spacetime with the precision required to study spacetime foam directly. The distances involved at the quantum scale are so small, on the order of the Planck length, which is approximately 10 to the power of -35 meters, that even the most powerful particle accelerators, like the Large Hadron Collider, cannot probe this realm of spacetime. This limitation has led physicists to explore alternative methods of studying spacetime foam, such as examining the cosmic microwave background radiation or seeking evidence of quantum gravitational effects in black holes. While direct observation of space-time foam may be out of reach for now, there are promising avenues for indirect detection. One of the most exciting possibilities involves the study of high-energy cosmic events, such as gamma-ray bursts, or the merging of black holes. These events may produce quantum gravitational effects that could leave detectable signatures in the data we collect from telescopes and observatories. In particular, the detection of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, has opened up new possibilities for observing the structure of spacetime itself. Gravitational waves were first predicted by Einstein in 1915, and their detection in 2015 marked a milestone in our ability to observe the very fabric of spacetime. It's possible that in the future, we may detect more subtle gravitational waves that could reveal the foamy nature of spacetime. The exploration of spacetime foam also raises the tantalizing possibility of alternate realities or parallel universes. Some theories suggest that the quantum fluctuations in spacetime might create bubbles of spacetime that could potentially contain their own separate universes. These universes could have different physical laws or constants, giving rise to entirely distinct realities. This idea, known as the multiverse theory, is still highly speculative, but the connection to space-time foam offers a new avenue for exploring the potential existence of other universes. The concept of the multiverse also ties into some of the most profound questions in philosophy and metaphysics. If space-time foam is indeed the fabric from which our universe, and potentially many others, is woven, it could have implications for the nature of reality itself. What does it mean for us to exist in this particular universe, in this particular configuration of space-time? Are we the product of a random fluctuation in the foam of space-time, or is there a deeper underlying purpose to the structure of the cosmos? These questions move beyond the realm of science and into the territory of existential contemplation, blurring the line between physics and philosophy. Another fascinating aspect of space-time foam is its potential connection to time itself. Time, as we experience it, seems to flow in a linear fashion from past to present to future. However, when we look at the quantum realm, the nature of time becomes far more ambiguous. In quantum mechanics, time is often treated as a parameter rather than a physical entity, and there is no clear understanding of how time behaves at the Planck scale, where quantum fluctuations in spacetime occur. If spacetime is indeed foamy, it's possible that time itself might not be as fixed as we perceive it. The fluctuations in spacetime foam could potentially cause time to behave in ways that are currently unimaginable, such as allowing for time travel or creating loops in time where cause and effect become entangled. The potential implications of spacetime foam for time and the fabric of reality are staggering. If the fluctuations in spacetime are truly the foundational elements of the universe, then understanding their nature could lead to a complete reevaluation of the laws that govern everything from particle interactions to the flow of time itself. We could find ourselves facing a new understanding of the universe, one where the boundaries between the past, present, and future become less rigid and more interconnected. One intriguing possibility that arises from these considerations is the potential for manipulating space-time foam to achieve seemingly impossible feats. If we can manipulate the quantum fluctuations of space-time, could we, in theory, create shortcuts through space, allowing for faster-than-light travel? Could we develop technologies that allow us to bend the fabric of space-time to our will, opening up the possibility of interstellar travel, or even instantaneous communication across vast distances? While these ideas may seem far-fetched today, the exploration of space-time foam could be the key to making such advancements a reality in the distant future. The mysteries of space-time foam offer a glimpse into a universe that is far more complex and interconnected than we currently understand. The idea that the very fabric of space-time is foamy and fluctuating at quantum scales challenges our perceptions of reality and raises questions that have the potential to revolutionize our understanding of the cosmos. As we continue to explore this enigmatic and dynamic aspect of the universe, we may uncover truths that completely reshape our view of the world and our place within it. As we continue exploring the implications of space-time foam, it's essential to consider how these quantum fluctuations might influence the broader structure of the universe. While the concept of space-time foam may initially seem abstract or disconnected from the observable universe, its impact on everything we experience could be profound. These fluctuations might not only affect the smallest scales of spacetime but could also ripple outward to shape the behavior of galaxies, stars, and even the fundamental constants of physics. The frothy nature of spacetime suggests that the universe is far from the stable, smooth entity we once believed it to be. Instead, it is a highly dynamic, ever-changing system, where even the fabric of spacetime itself is subject to fluctuations. In this sense, spacetime foam could offer new insights into the structure and behavior of the universe on the largest scales. For example, it could influence the distribution of dark matter and dark energy, the mysterious substances that make up most of the universe's mass energy content. Dark matter, which doesn't emit or interact with electromagnetic radiation, can't be directly observed, but its presence is inferred from its gravitational effects on visible matter. Dark energy, meanwhile, is believed to be responsible for the accelerated expansion of the universe. While we know very little about these components of the cosmos, some researchers have suggested that the fluctuations in spacetime foam might play a role in the distribution and behavior of dark matter and dark energy. Perhaps the quantum fluctuations that occur at the Planck scale could provide a more nuanced understanding of these enigmatic phenomena, shedding light on the dark forces that govern the cosmos. This idea opens up fascinating possibilities for future research. If space-time foam is indeed influencing the large-scale structure of the universe, then understanding its nature could lead to a breakthrough in our understanding of cosmology. For example, if we can study how space-time fluctuations interact with dark matter, we may be able to detect new types of particles or forces that were previously hidden from view. Similarly, if space-time foam affects the behavior of dark energy, we might uncover new ways to manipulate, or even harness this mysterious force. In the search for answers, one key area of investigation lies in the study of the very early universe. The moments following the Big Bang, when the universe was in its infancy, were likely dominated by extreme quantum fluctuations. During this period, space-time itself may have been more chaotic and frothy than at any other point in history. By studying the quantum fluctuations that occurred during this primordial phase, we may be able to gain new insights into how the universe evolved and how space-time foam plays a role in shaping its large-scale structure. Researchers are also exploring how the study of space-time foam could offer new insights into the behavior of black holes. Black holes, those enigmatic regions of space-time where gravity is so intense that not even light can escape, have long been a subject of fascination and mystery. Their event horizons, the boundaries beyond which nothing can return, are key to understanding the nature of space-time itself. As we probe deeper into the behavior of black holes, space-time foam could offer a new way to think about their formation and evolution. Could the fluctuations of space-time at the quantum level contribute to the creation of black holes? Or might they offer clues about what happens inside these cosmic prisons? These are questions that researchers are working hard to answer, and space-time foam might hold the key to unlocking the deepest mysteries of black holes. In addition to its implications for dark matter, dark energy, and black holes, space-time foam also presents a tantalizing connection to another of the universe's greatest mysteries, the nature of time itself. As we've seen, time as we experience it appears to flow in a continuous, linear fashion. But at the quantum level, time becomes less certain. In the context of space-time foam, time might not behave in the way we typically expect it to. Quantum fluctuations could cause time to jump in discrete steps or even behave in a nonlinear fashion, where the past, present, and future become blurred. The relationship between space-time foam and time is one of the most intriguing and perplexing aspects of this concept. If space-time is indeed frothy, with continuous fluctuations at the quantum level, could it be that the very flow of time is also subject to these fluctuations? Could these quantum jitters in space-time give rise to phenomena like time loops, where the past and future become entangled in ways that challenge our understanding of causality? The idea of time being affected by the quantum foam of space-time opens up the possibility of time travel, though this remains speculative and theoretical. Time travel, in particular, is an idea that has fascinated scientists, philosophers, and science fiction enthusiasts for generations. While it remains firmly in the realm of theoretical physics, the study of space-time foam could offer a potential pathway toward understanding how time travel might work. If the fluctuations in space-time can create loops or distortions in the fabric of time, it's conceivable that these bends in space-time could allow for travel backward or forward in time, much like the wormholes we've discussed earlier. These time-altering phenomena might be subtle and rare, but the very possibility of their existence challenges our conventional understanding of the universe and raises profound questions about the nature of reality. Moreover, these fluctuations in space-time might also influence other strange and counterintuitive phenomena, such as the idea of quantum tunneling. Quantum tunneling occurs when particles move through barriers that, according to classical physics, they shouldn't be able to pass. This behavior is one of the key features of quantum mechanics, and it has been observed in a variety of contexts, from nuclear fusion in stars to the functioning of transistors and modern electronics. The connection between quantum tunneling and space-time foam is still being explored, but it's possible that the fluctuating nature of space-time at the quantum level could enable or enhance tunneling phenomena, allowing particles to bypass barriers or enter alternate regions of space-time. As we continue to unravel the mysteries of space-time foam, it's clear that we are on the cusp of a deeper understanding of the universe. Every discovery about the structure of spacetime brings us one step closer to unlocking the fundamental laws that govern the cosmos. Whether it's through advances in quantum gravity, insights into dark matter and dark energy, or breakthroughs in our understanding of black holes and time, spacetime foam could be the key that unites the many puzzles of the universe. While we may not yet be able to observe the foam directly, the very concept pushes the boundaries of what we know and challenges us to rethink the nature of reality. We are entering a new era of scientific exploration, one where the mysteries of spacetime, gravity, and the universe itself are closer than ever to being understood. Whether or not spacetime foam holds the key to the ultimate theory of everything, it's undoubtedly one of the most exciting frontiers in the search for knowledge. Every step we take in this journey has the potential to reveal something extraordinary about the cosmos, reshaping our view of the universe in ways we can't yet imagine. As we continue to probe the implications of spacetime foam, one of the most intriguing aspects to consider is how it might reshape our understanding of the cosmos at both the smallest and largest scales. The frothy nature of spacetime could influence not just the very fabric of the universe, but also the behavior of the fundamental forces that govern it, including gravity, electromagnetism, and the weak and strong nuclear forces. In particular, the way spacetime foam interacts with gravity could provide new insights into the nature of gravity itself, potentially leading to groundbreaking discoveries in our understanding of the force that shapes the structure of the universe. Gravity, as we know it, is a force that operates on massive scales, governing the motion of planets, stars, and galaxies. At the level of everyday experience, gravity appears as a smooth, continuous force, pulling objects toward each other in a predictable manner. However, at the quantum level, things become far more complicated. Quantum gravity, the study of gravity in the context of quantum mechanics, is one of the most challenging areas of modern physics. The nature of gravity at the Planck scale, where quantum fluctuations of spacetime occur, remains poorly understood. Could spacetime foam provide a new way to understand the relationship between gravity and quantum mechanics? One possibility is that spacetime foam could act as a medium through which gravity propagates. Instead of being a smooth, continuous force, gravity might be transmitted through the fluctuations in spacetime itself. This would imply that gravity, like other fundamental forces, is not an intrinsic property of objects or particles, but instead a manifestation of the underlying structure of spacetime. If this idea holds true, it could lead to new ways of thinking about gravity, potentially reconciling general relativity, the theory that describes gravity on large scales, with quantum mechanics, which governs the behavior of particles on the smallest scales. This would be a significant step toward the long-sought theory of everything, a unified framework that combines all the forces of nature into a single, coherent theory. The idea that spacetime foam could play a role in gravity is not just speculative. Recent advances in quantum gravity, such as the study of loop quantum gravity and string theory, have suggested that spacetime itself is quantized, meaning that it is composed of discrete units, or chunks, at the Planck scale. These models propose that spacetime is not a smooth, continuous medium but is instead made up of small, discrete building blocks that interact with each other in complex ways. In this context, spacetime foam could be seen as a manifestation of these quantum fluctuations, providing a new way to understand the behavior of gravity at the smallest scales. Furthermore, the study of spacetime foam could offer new insights into the nature of black holes. As we mentioned earlier, black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. However, the quantum mechanical nature of spacetime suggests that the event horizon of a black hole, the boundary beyond which nothing can return, might not be as rigid and impenetrable as we once thought. Instead, it could be subject to fluctuations at the quantum level, potentially allowing for new types of interactions between the black hole and the surrounding spacetime foam. These interactions might shed light on the mysterious interior of black holes, where gravity becomes so strong that our current theories of physics break down. One of the most perplexing questions about black holes is what happens to information that falls into them. According to classical physics, once something crosses the event horizon, it is lost to the universe forever. However, this creates a paradox, because quantum mechanics suggests that information can never be destroyed. This conundrum, known as the black hole information paradox, has led scientists to propose that the quantum nature of spacetime could provide a solution. If spacetime is indeed foamy and subject to fluctuations at the quantum level, it's possible that information could be preserved in these fluctuations, potentially allowing it to be retrieved in the future. This idea, while still highly speculative, could provide a resolution to one of the most fundamental problems in modern physics. Another area where spacetime foam might offer new insights is in the study of the very early universe. As we look back to the moment of the Big Bang, we encounter a time when the universe was hot, dense, and filled with quantum fluctuations. At this point in the universe's history, spacetime itself was likely in a highly dynamic and foamy state, with fluctuations occurring on extremely small scales. These fluctuations could have played a crucial role in shaping the large-scale structure of the universe, influencing the formation of galaxies, stars, and planets. By studying the quantum properties of spacetime during this early period, we could gain new insights into the origins of the universe and the forces that shaped its evolution. The study of spacetime foam also has implications for the search for new types of particles and forces. While we are familiar with the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, there may be other forces or particles lurking in the background, waiting to be discovered. The fluctuating nature of spacetime could provide a fertile ground for the creation of new particles or forces, possibly leading to the discovery of phenomena that are completely outside of our current understanding of physics. For instance, some theories suggest that spacetime foam could give rise to exotic particles, such as gravitons, the hypothetical particles that mediate the force of gravity. Gravitons have never been directly detected, but their existence is predicted by many quantum gravity theories. If spacetime foam can interact with gravitons in novel ways, this could provide new avenues for detecting these elusive particles. In the future, experiments designed to probe the quantum properties of spacetime, such as those conducted at particle accelerators like the Large Hadron Collider, LHC, may yield new discoveries that reveal hidden aspects of the universe. In addition to the search for new particles, spacetime foam could also have profound implications for the study of dark matter and dark energy. As we've seen, these mysterious substances make up the vast majority of the universe's mass and energy, yet we know very little about them. The fluctuations in spacetime could be related to the behavior of dark matter, influencing how it interacts with other forms of matter and energy. Similarly, spacetime foam might play a role in the acceleration of the universe's expansion, offering new insights into the nature of dark energy and how it drives the cosmos to expand at an ever-increasing rate. By understanding the quantum structure of spacetime, we may be able to unlock the secrets of these dark forces and develop new theories that explain their existence. This, in turn, could lead to a deeper understanding of the fundamental nature of the universe and our place within it. The study of spacetime foam is not just about understanding the tiny, invisible fluctuations that occur at the Planck scale, it's about understanding the very fabric of the universe itself, and how it shapes everything we observe. As we reach the frontier of spacetime foam, we are reminded of how much we have yet to learn about the universe. The mysteries of spacetime, gravity, and quantum mechanics are intertwined in ways that we are only beginning to comprehend. Every new discovery brings us closer to a unified theory of physics, one that could explain everything from the tiniest particles to the largest galaxies. Whether through advances in quantum gravity, new insights into black holes, or breakthroughs in our understanding of dark matter and dark energy, the study of spacetime foam could be the key to unlocking the deepest secrets of the cosmos. The journey of exploring spacetime foam is just beginning. While we may not yet have all the answers, the questions themselves are both profound and exciting. As scientists continue to probe the nature of spacetime at the smallest scales, they are pushing the boundaries of our understanding and opening new frontiers for exploration. What we discover in the coming years may well change the way we see the universe forever. As we continue our exploration into the frothy nature of spacetime, it's important to consider the broader implications of these ideas. The study of spacetime foam and its quantum fluctuations is not just a theoretical exercise. It is at the heart of a deeper understanding of the universe itself, one that challenges our most fundamental assumptions about reality. The very concept of space-time foam forces us to reconsider how we think about the fabric of the cosmos. For centuries, we have viewed space as an empty, inert backdrop against which events unfold. Time, in a similar vein, has often been treated as a linear progression, like a river flowing in one direction. But quantum mechanics, with its probabilistic nature and its strange behaviors, reveals a very different picture, one where space and time are not separate, immutable entities, but rather dynamic, constantly evolving properties that respond to the presence of energy and matter. Space-time foam is not simply a mathematical abstraction or a theoretical curiosity. It is the very manifestation of the quantum nature of the universe. One of the key aspects of space-time foam is that it introduces an inherent uncertainty to the structure of space-time itself. This uncertainty stems from the fact that, at the Planck scale, space-time is no longer smooth and continuous, but is instead subject to fluctuations. These fluctuations are incredibly small, but their effects could be profound. They could influence the behavior of light, gravity, and even the fundamental forces that govern particle interactions. In this sense, space-time foam is a realization that the universe is not as fixed as we once thought. Its very fabric is in constant flux, subject to the whims of quantum mechanics. As researchers continue to investigate these fluctuations, they are starting to probe the possibility that space-time foam could be at the root of some of the most perplexing phenomena in the universe. For instance, one of the central mysteries in modern physics is the apparent conflict between quantum mechanics and general relativity. While quantum mechanics accurately describes the behavior of particles on small scales, and general relativity provides an excellent framework for understanding gravity on large scales, the two theories are fundamentally incompatible. Space-time foam may provide the bridge that links these two realms, helping to resolve the conflict between quantum mechanics and gravity. By understanding how space-time behaves at the quantum level, we may one day be able to reconcile the two theories and develop a unified theory of quantum gravity. This theory, often referred to as the Holy Grail of modern physics, would not only provide a deeper understanding of gravity but could also shed light on other cosmic phenomena. One of the most intriguing aspects of space-time foam is its potential connection to the behavior of black holes. These enigmatic objects, which are formed when massive stars collapse under their own gravity, are known for their extreme gravitational forces. However, their interiors remain shrouded in mystery. The quantum fluctuations of spacetime could hold the key to understanding what happens inside black holes, potentially resolving the black hole information paradox that has puzzled physicists for decades. The black hole information paradox arises from the fact that, according to classical physics, any information that falls into a black hole is lost to the universe. However, quantum mechanics dictates that information cannot be destroyed. This apparent contradiction has led scientists to propose that, instead of information being lost, it might be encoded in the quantum fluctuations of spacetime itself. If spacetime is indeed foamy, the fluctuations within it could carry the information that falls into a black hole, preserving it in a form that we do not yet fully understand. This could provide a resolution to one of the most perplexing issues in modern physics, and open up new avenues for understanding the true nature of black holes. Beyond black holes, spacetime foam could also offer insights into the nature of the early universe. As we look back to the time of the Big Bang, we encounter a universe that was not only incredibly hot and dense, but also deeply chaotic. At this point in time, the universe was filled with quantum fluctuations that were much more significant than they are today. These fluctuations could have played a crucial role in the formation of the large-scale structure of the universe, influencing the formation of galaxies, stars, and other cosmic structures. The study of spacetime foam could help us understand how these fluctuations shaped the universe in its infancy, and provide clues about the origins of the cosmos itself. In fact, the idea that spacetime could be foamy and dynamic at the quantum scale has profound implications for our understanding of the Big Bang. The early universe, which was initially in a state of extreme density and temperature, was governed by the laws of quantum mechanics. During this time, spacetime itself may have been fluctuating on incredibly small scales, creating a chaotic and turbulent environment. These fluctuations could have contributed to the rapid expansion of the universe in the moments after the Big Bang, a process known as cosmic inflation. The study of space-time foam could help us understand how these fluctuations gave rise to the cosmic inflationary period and shaped the evolution of the universe in its early stages. In addition to the early universe, space-time foam could also provide a new perspective on the search for dark matter and dark energy. These mysterious components of the universe make up most of the mass and energy in the cosmos, yet we still know very little about them. The fluctuating nature of spacetime could play a role in the behavior of dark matter, potentially explaining how it interacts with visible matter and gravity. Similarly, the strange properties of spacetime foam might provide new insights into the nature of dark energy, the enigmatic force responsible for the accelerated expansion of the universe. The existence of dark matter and dark energy has led to some of the most profound questions in modern cosmology. We know that dark matter exerts gravitational effects on visible matter, such as galaxies and galaxy clusters, but we have yet to detect it directly. Similarly, dark energy appears to be driving the accelerated expansion of the universe, but we have no clear understanding of what it actually is. Space-time foam may hold the key to understanding these phenomena, offering new ways to probe the quantum nature of the universe and potentially leading to groundbreaking discoveries about the dark components of the cosmos. As we continue to explore space-time foam, we are reminded of the vastness of what we still don't know. The mysteries of the universe are deeper than we can imagine, and every new discovery opens up more questions. But in these questions lies the promise of discovery, the potential to uncover the hidden structures and forces that govern the cosmos. The study of space-time foam is just one piece of the puzzle, but it is a crucial one. As scientists continue to probe the quantum nature of space-time, we may be on the cusp of a revolution in our understanding of the universe. The more we learn about the foamy nature of space-time, the more we realize that the universe is far more complex and mysterious than we ever imagined. The very fabric of reality, it seems, is not smooth and continuous, but is a dynamic, fluctuating medium that shapes everything around us. These fluctuations may be the key to understanding some of the most profound mysteries of the cosmos, from black holes to the origins of the universe itself. As we push the boundaries of our understanding, we may one day discover that the universe is even more strange and wondrous than we can currently conceive. Space-time foam is just one of many concepts that could lead us to these discoveries, and its study may one day unlock the deepest secrets of the cosmos. The road ahead is long and uncertain, but with each new step, we are getting closer to understanding the true nature of reality. As we continue to explore the nature of space-time foam and its role in the fabric of the universe, it's essential to understand how this concept fits into the broader landscape of modern physics. The strange, frothy structure of space-time challenges many of the assumptions we've held for centuries. If space-time is indeed a dynamic and fluctuating entity, then our entire understanding of the universe may need to be rethought. One of the major hurdles in understanding space-time foam is the lack of direct observational evidence. Unlike more traditional phenomena that we can measure or observe through telescopes and experiments, space-time foam operates at scales that are far beyond our current technological capabilities. The Planck scale, the scale at which quantum gravitational effects become significant, is incredibly small, on the order of meters. This is many orders of magnitude smaller than the smallest length scales that current particle accelerators can probe. As a result, scientists must rely on indirect evidence and theoretical models to study this mysterious aspect of spacetime. While we cannot directly observe spacetime foam, its effects may manifest in other ways. For instance, some researchers have speculated that spacetime fluctuations could cause subtle distortions in the propagation of light over vast distances. This could potentially be detected through observations of distant cosmic objects such as gamma-ray bursts or quasars. If the light from these objects travels through a foamy spacetime, the fluctuations could distort the light in ways that we can measure. These distortions, although extremely small, could provide crucial evidence for the existence of spacetime foam and help scientists test the predictions of quantum gravity theories. Another possibility is that spacetime foam could leave an imprint on the cosmic microwave background (CMB), the faint radiation left over from the Big Bang. The CMB provides a snapshot of the universe when it was just 380,000 years old, and it carries with it information about the early conditions of the universe. If space-time was indeed foamy during this time, it could have influenced the patterns we observe in the CMB. By analyzing these patterns in greater detail, scientists may be able to detect signs of quantum fluctuations in space-time, providing another indirect way of studying space-time foam. In addition to these observational strategies, theoretical physicists have been developing a variety of mathematical models to describe the behavior of space-time at the quantum level. One of the most well-known approaches is loop quantum gravity, LQG, which seeks to describe gravity in a way that is consistent with the principles of quantum mechanics. According to LQG, space-time is composed of discrete units, or quantum loops, that form the fabric of the universe. These loops are thought to be linked together in a network, and the behavior of space-time at the Planck scale can be understood in terms of these quantum loops. In this framework, space-time foam would be the result of the interactions between these loops, which fluctuate and change over time. Another approach is string theory, which posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. According to string theory, space-time itself may have extra dimensions beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions could be curled up on extremely small scales, contributing to the foamy structure of space-time. In this view, space-time foam arises from the interactions of strings and the higher dimensional structure of space-time. While string theory is still a work in progress and remains speculative, it offers a promising avenue for understanding the quantum structure of space-time. Beyond the mathematical models, the study of space-time foam also raises profound philosophical questions about the nature of reality. If space-time is truly foamy, with constant fluctuations and a dynamic, uncertain structure, then what does this mean for our understanding of causality and determinism? In classical physics, the idea that events unfold in a deterministic manner, where one state follows another in a predictable way, is a cornerstone of our understanding of the universe. However, the quantum nature of spacetime suggests that this idea may not apply at the smallest scales. The fluctuations in spacetime could introduce an element of indeterminacy into the fabric of reality itself, challenging our classical notions of cause and effect. This brings us to another fascinating possibility: the connection between spacetime foam and the nature of time itself. In many quantum gravity theories, time is not a fixed, unchanging entity, but rather something that can emerge from the underlying quantum structure of spacetime. If spacetime is foamy and dynamic at the Planck scale, then time itself may be subject to fluctuations. These fluctuations could potentially manifest as jumps or discrete moments in the flow of time, leading to a new understanding of the concept of time. Instead of being a smooth, continuous river, time may be more akin to a series of discrete steps or events, each one influenced by the quantum structure of spacetime. These ideas are still highly speculative, but they point to the possibility that our conventional understanding of time and causality is incomplete. By exploring the nature of spacetime foam, we may one day be able to develop a more complete theory of time, one that is consistent with the principles of quantum mechanics and general relativity. Such a theory would not only revolutionize our understanding of the universe but could also have profound implications for how we perceive our own place in the cosmos. Of course, the study of space-time foam also has practical implications for other areas of physics and technology. For example, the understanding of spacetime at the quantum level could lead to new insights into the behavior of particles and fields, potentially leading to breakthroughs in areas such as quantum computing, high-energy physics, and even the development of new technologies based on the principles of quantum mechanics. The discovery of spacetime foam could also open up new possibilities for the exploration of the universe, allowing us to probe the deepest reaches of space and time in ways that were previously unimaginable. The concept of spacetime foam represents a bold and exciting frontier in our understanding of the universe. It challenges many of our most fundamental assumptions about the nature of space, time, and reality itself. While the idea of a foamy, fluctuating spacetime may seem strange or counterintuitive, it is rapidly becoming a key component of modern theoretical physics. As our understanding of this dynamic structure grows, we may uncover new insights into the most profound mysteries of the cosmos: black holes, dark matter, the early universe, and the nature of time itself. Space-time foam, though still largely theoretical, offers us a glimpse into the quantum heart of the universe. The more we learn about these quantum fluctuations, the closer we come to unraveling the deepest secrets of the cosmos. The implications of space-time foam extend far beyond the confines of academia. They touch upon the very nature of reality, challenging our perception of space, time, and existence itself. As we continue to explore this foamy, dynamic fabric of space-time, we may one day find ourselves at the threshold of a new understanding of the universe, one that transcends the boundaries of space and time, revealing a reality far more complex and mysterious than we ever imagined. As we continue to dive deeper into the concept of space-time foam, it's essential to appreciate the underlying connection between quantum mechanics and general relativity, the two pillars of modern physics that have, until now, remained somewhat isolated. One of the most challenging aspects of understanding space-time foam is the effort to reconcile these two frameworks. Quantum mechanics operates at the smallest scales, where particles and fields exhibit wave-like behavior and uncertainty, while general relativity governs the macroscopic scale, dictating how massive objects like planets, stars, and even galaxies behave within the fabric of space-time. Space-time foam lies at the intersection of these two realms, where the effects of both quantum mechanics and general relativity are expected to become significant. At the heart of this issue is the question of how gravity behaves at the quantum level. According to general relativity, gravity is not a force in the traditional sense but a manifestation of the curvature of space-time caused by the presence of mass and energy. Massive objects warp the fabric of space-time, and this curvature is what we perceive as gravity. However, general relativity does not account for quantum effects, and quantum mechanics, in turn, does not incorporate gravity. The resulting disconnect between these two theories has been one of the biggest challenges in modern physics. Space-time foam, as a potential manifestation of quantum gravity, offers a possible solution to this problem. By examining the fluctuations in space-time at the Planck scale, physicists hope to uncover a quantum theory of gravity that can describe how the curvature of space-time behaves on the smallest scales. This theory would not only allow us to understand the structure of space-time foam but also provide a more complete picture of the universe, bridging the gap between quantum mechanics and general relativity. One of the key insights that space-time foam provides is that space-time is not a continuous, smooth entity, as we often imagine it, but rather something that is fundamentally granular and fluctuating. This challenges our classical notions of space and time, which assume that space-time is a static backdrop against which events unfold. In the quantum realm, however, space-time is dynamic, with fluctuations occurring constantly at the smallest scales. These fluctuations could be responsible for the creation of virtual particles, the brief and fleeting particles that spontaneously appear and disappear in empty space according to the principles of quantum mechanics. These virtual particles are an essential feature of quantum field theory, and their interactions could be a crucial element in the formation of space-time foam. When these particles interact with each other, they could create distortions in the fabric of space-time, leading to the foamy structure that we observe in theoretical models. The constant fluctuation of space-time, driven by the interactions of virtual particles, could also explain phenomena like the uncertainty principle, which states that certain properties of particles, such as position and momentum, cannot be simultaneously known with absolute precision. At the Planck scale, space-time itself may be subject to this kind of uncertainty, making it impossible to precisely define the structure of space-time at any given moment. The concept of space-time foam also suggests that the universe at its most fundamental level may be far more complex than we can currently imagine. If space-time is truly foamy and fluctuating, then the very nature of reality may be shaped by these quantum fluctuations. The smooth, continuous space we experience in our everyday lives may simply be an emergent property of these fluctuations, much like the smoothness of the surface of the ocean is an emergent property of the chaotic motion of individual water molecules. In this view, the universe as we know it is an illusion, one that arises from the underlying quantum structure of space-time. This idea raises profound questions about the nature of reality itself. If space-time is a frothy, fluctuating medium, then what does this imply about the fundamental nature of existence? Are the events we experience in our daily lives real, or are they merely the result of statistical fluctuations in a far more complex and uncertain underlying reality? These are questions that philosophers and physicists alike have pondered for centuries, and the discovery of space-time foam may offer new insights into these age-old debates. Moreover, the idea that space-time is not static but constantly fluctuating also has implications for the way we understand the concept of causality. In classical physics, causality is a bedrock principle. Events unfold in a predictable, cause-and-effect manner. However, in the quantum world, events are governed by probabilities rather than certainties. If space-time itself is subject to fluctuations at the quantum level, then it may not behave in a deterministic way. Instead, the fabric of space-time could be governed by a kind of probabilistic randomness, with events unfolding in ways that are influenced by the underlying quantum fluctuations of space-time. This uncertainty in the fabric of space-time could also have profound implications for the way we understand the flow of time. In classical physics, time is a continuous, linear progression from past to present to future. However, if space-time is foamy and fluctuating, then time itself may not flow smoothly. Instead, it could be subject to discrete jumps or shifts, as the fluctuations in space-time introduce irregularities in the passage of time. This could lead to a new understanding of time, one that challenges our classical notions of the past, present, and future. To fully grasp the significance of space-time foam, we must also consider its potential connections to other phenomena in the universe. One such connection is the behavior of black holes, which are regions of space-time where gravity is so strong that not even light can escape. Black holes are some of the most extreme environments in the universe, and their study has provided valuable insights into the nature of space-time and gravity. It is thought that the quantum effects of space-time foam may play a crucial role in the behavior of black holes, particularly in the context of the information paradox. The information paradox is a long-standing problem in theoretical physics that arises from the idea that information that falls into a black hole is lost forever. According to the laws of quantum mechanics, information cannot be destroyed, but the intense gravitational forces near a black hole seem to prevent any information from escaping. Some physicists believe that space-time foam could hold the key to resolving this paradox. The fluctuations in space-time could provide a mechanism for information to escape from black holes, potentially offering a way to reconcile the laws of quantum mechanics with the behavior of black holes. Another intriguing connection is the potential relationship between space-time foam and the elusive concept of dark matter. Dark matter is a mysterious substance that is thought to make up a significant portion of the universe's mass, yet it has never been directly detected. Its existence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. Some researchers have proposed that the fluctuations in space-time caused by space-time foam could be responsible for the effects that we attribute to dark matter. If the fabric of space-time is foamy and fluctuating, it could exert an influence on matter that behaves in ways similar to dark matter, potentially offering a new avenue for understanding this mysterious substance. As we continue to explore the nature of space-time foam and its potential implications for our understanding of the universe, it becomes clear that this concept touches on some of the most profound questions in physics and philosophy. From the structure of space-time itself to the behavior of black holes, the passage of time, and even the nature of reality, space-time foam offers a tantalizing glimpse into the quantum heart of the universe. While much of this is still speculative, the potential for groundbreaking discoveries in this field is enormous. The more we learn about the fluctuating, foamy nature of space-time, the closer we come to unlocking some of the deepest mysteries of the cosmos, perhaps revealing a universe far more intricate and mysterious than we could ever have imagined. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.